Hello friends, I welcome you in lecture number 1 on method of separation of variables. This method we are going to discuss for the solution of partial differential equations. We have discussed partial differential equations and their solutions in different ways. We have discussed how to solve first order partial differential equations. There is one playlist for the solution of first order partial differential equations, and we have also discussed how to obtain solution of higher order partial differential equations, in which we have discussed two cases for homogeneous and non-homogeneous partial differential equations. From this lecture onwards, we are going to discuss this special method which is known as method of separation of variables for solving certain types of partial differential equations. So here we assume that for this method partial differential equation is homogeneous and linear. We have discussed the meaning of homogeneous partial differential equation and linear partial differential equation in the playlists of first order as well as higher order partial differential equations. So general form of homogeneous linear partial differential equation, which we have written in earlier lecture series, is fdd-z equal to 0, where z is a function of x and y. So we are interested in the solution of homogeneous linear partial differential equation using method of separation of variables. In this lecture we will see how this method works and when it is applicable. So to apply this method, we assume that given partial differential equation is linear and homogeneous. Given PD is a homogeneous and linear. For example, if I am writing del u by del x equal to 4 times del u by del y, then this is homogeneous. Homogeneous PD means every term of the equation contains the dependent variable or its derivatives. Here this term contains partial derivative of dependent variable u with respect to x. This is also containing partial derivative of dependent variable u with respect to y. So this is homogeneous. Suppose I am writing here plus u, then this is also homogeneous. But if I am writing del u by del x equal to 4 into del u by del y plus e raised to x plus 2y, then this is non-homogeneous partial differential equation, because this term is not containing dependent variable or its derivatives. So PD is homogeneous if each of its terms contains either dependent variable or its derivatives, and linear means the dependent variable and its derivatives are in the first degree only and they are not multiplied together. Now once we have homogeneous and linear partial differential equation, we are able to apply the method of separation of variables, and for that we assume that solution of given partial differential equation is in this form. Suppose our dependent variable is u and independent variables are x and y in a given partial differential equation. Then we are interested in the value of u which satisfies given partial differential equation. So we will assume that given differential equation has solution of the form capital X into capital Y. That is, the solution is the product of functions of x and y. It is the product of function of x only into function of y only. So for this method, this will be a very first step. We will always assume that given partial differential equation has a solution of this type of product form, or it has a product form solution. So we are familiar, we assume that equation has solution in this form. So now we know that if u is solution, then it must satisfy the given differential equation. So we will put value of this u in the given differential equation, and the method will work in that way. So we will understand the method with the help of example. I have taken this example here. Solve the following partial differential equation with the method of separation of variables. So you can see here we have partial derivatives of z with respect to x and y. That means we are interested in the unknown function z which satisfies this homogeneous linear partial differential equation. So we will start with the assumption that solution of this equation is in this form: capital X into x times capital Y into y, where capital X and capital Y both are functions of x and y alone. Capital X is a function of x only, capital Y is a function of y only. So this is the assumption. We will start the method with this assumption that given equation has solution in this form. Now because this is the solution of this equation, it will satisfy this equation, and here we require partial derivatives of x and y, partial derivatives of z with respect to x and y. Del z by del x means we are differentiating partially with respect to x. So we will consider capital Y as constant, and this is dx by d small x, y is constant. Because x is function of x only and we are differentiating with respect to x, so this is ordinary derivative that we will denote by this symbol dash, x dash y. X dash means it denotes derivative with respect to small x. If I am interested in the second order derivative, then again I will differentiate this with respect to x considering y as constant. That means I have to write second order derivative d square x by dx square times y, that I can rewrite as x double dash y. Similarly, del z by del y, for partial derivative with respect to y, we consider x as constant, and derivative of capital Y with respect to small y, that is x into y dash. So now we have del z by del x, which is x dash into y, del z by del y, which is x into y dash, and del square z by del x square, which is x double dash into y. And z is a solution of this equation, so we will substitute these values in this equation, and we will obtain ordinary differential equations in capital X and capital Y, that we will solve in capital X and capital Y, and finally we will put values of x and y in this product solution. That will be our final solution. This is the main idea of the method. You have to start every time with the assumption that given equation has solution in this form. Then you find out the derivatives of given dependent variable with respect to given independent variables and substitute them into given equation, and after simplification you will have ordinary differential equations in these two variables, and after solving those two ordinary differential equations you will be able to decide this product solution. I have solved this problem here step by step. I have written here. So first I have written given partial differential equation. I give it number 1 and I assume that given equation has solution of the form z equal to capital X into capital Y, where x is a function of x alone and y is a function of y alone. Now once this is the solution of equation 1, it must satisfy equation 1. So I have obtained del z by del x, del z by del y, and del square z by del x square. and then I substitute all these values in equation 1. So in equation 1 we have del square z by del x square, that is x double dash y minus 2 times del z by del x, minus 2 times del z by del x is x dash y, and plus del z by del y, that is x y dash. So that I have written here. After that I can take y common from these two terms, and I will have x double dash minus 2x dash times y, and I transfer this term on the right hand side. Now here capital X is function of x only and capital Y is function of y only. So I try to separate the variables. So for that I transfer this x on the left hand side and this y is transferred on the right hand side, and I obtain this equation: x double dash minus 2x dash divided by x equal to negative of y dash over y. Now here we know that capital X is a function of only one variable small x, capital Y is also a function of another variable small y. So these two also are functions of x. This is also going to be a function of x and this is also going to be a function of y. So we have this type of situation: some function of x, this is going to be a function of x, say f of x, and here also I have another function of y, say g of y. So we have two functions here which are equal, and x and y are independent variables. So this is possible if and only if both the functions are equal to some constant, say k. If value of both the functions is equal to some fixed constant, then only this is possible. That means both the functions must be equal to constant, same constant. Suppose they are not equal to same constant. Suppose this one is constant, suppose fx is constant and this is non-constant, then that is not possible because both are equal. Suppose fx is constant and gy is not non-constant, then they are not going to be equal. So this is possible if and only if these both functions are equal to some constant, and this type of situations we will always have after substituting values of derivatives in the given equation. So this is the common part for every problem. Here I have written that it is necessary that both sides of equation 3 must be equal to the same constant. Otherwise, if one independent variable, say x, were kept fixed and the other were allowed to vary, the left hand side of 3 would remain unchanged while the other varied, thus violating the equality. That is what I have explained, that suppose this is variable and this is kept fixed, then this is variable and this is constant, but here both are equal, so that is not possible. So two functions of two independent variables, two different independent variables are equal, and that is possible if and only if each of the functions are equal to same constant. So therefore we can write this is equal to some constant, say k, and this is also equal to same constant, say k. So here I have written that equation 3 can only be true if each side is equal to the same constant, say k. So we have written this is equal to k and this is equal to k. So now I have written these two equations, and this I can rewrite as x double dash minus 2x dash equal to kx, and then x double dash minus 2x dash minus kx equal to 0, and we keep this as it is. Now you can see capital X is a function of x only and capital Y is also a function of y only. Therefore equation 4 and 5 are ordinary differential equations. Equation 4 is ordinary differential equation. You can rewrite equation 4 as d square x by dx square minus 2 times dx by d small x minus k into x equal to 0. And we know how to solve this type of ordinary differential equation. This is homogeneous linear ordinary differential equation with constant coefficients. And if you have no idea about the ordinary differential equations, then you can visit my lecture series on ordinary differential equations. So to solve this equation number 4, we observe that this is homogeneous linear ordinary differential equation with constant coefficients. And to find out the solution of this equation, first we have to write down the characteristic equation or auxiliary equation for this number 4. For that, we replace second derivative by some second power of some constant, say m or variable, minus x dash is replaced by single power of m minus x is replaced by 1. So this is going to be the characteristic equation corresponding to this ordinary differential equation. To write down the characteristic equation, we replace nth derivative by nth power of m. So I have written here, that is called auxiliary equation or characteristic equation of equation 4 is m square minus 2m minus k equal to 0. And this is quadratic equation in variable m, and if we compare with a m square plus b m plus c equal to 0, we find that a is 1, b is minus 2 and c equal to minus k, and therefore solution is m equal to minus b is minus 2 plus or minus square root of b square, that is square of minus 2 minus 4 times a is 1 and c is minus k divided by 2 times a is 1. Now here if we simplify, this is negative negative positive, that is 2 plus or minus square of minus 2 is 4, here negative negative positive plus 4k divided by 2. Here also I can take 4 common, so I am left with 1 plus k and square root of 4 is 2, and these 2 will get cancelled and we are left with 1 plus or minus square root of 1 plus k, and k is a real constant, so we can say that roots are real and distinct. And we know that if roots of auxiliary equation are real and distinct, then our solution is in the form e raised to m into x. Here I have two different values of m, so I will write some arbitrary constant into e raised to m1x plus some another arbitrary constant into e raised to m2x. m1 will be 1 plus square root of 1 plus k and m2 will be square root 1 minus square root of 1 plus k. That I have written here. That is going to be the solution of equation number 4, in which dependent variable is capital X. So solution of this equation number 4 is x equal to c1 times e raised to 1 plus square root of 1 plus k. This is one value of m, and here negative sign another value of m, where c1 and c2 are arbitrary constants. Similarly, we have to solve equation number 5. Here dependent variable is y, and this is easy to solve. We can see we have a derivative of y in the numerator, and for that we apply this formula. If we have f dash x divided by fx, and if we want to integrate it, and then we write log of function in the denominator. So here I have derivative of y in the numerator. So if I integrate both sides with respect to small y, then integral is going to be minus ln y equal to integral of k with respect to y, that is k times y plus some arbitrary constant. So that I have written here. Integrating equation 5 with respect to y on both sides, we have ln capital Y equal to minus ky plus, instead of writing only constant, we have written log of the arbitrary constant, say C3. And now I transfer this on the left hand side, so that I have log y minus log C3 equal to minus ky. And using the property of logarithm, this I can rewrite as log of y divided by C3 equal to minus ky. And from this we find that capital Y over C3 equal to e to the power minus ky. Okay, we are applying this property. If I have log y equal to x, then y is going to be e to the power x. Here I have y over C3, that is e raised to minus ky, and finally I obtain capital Y equal to C3 times e raised to minus ky. This is the solution of this first order ordinary differential equation, equation number 5. Now once we find the values of capital X and capital Y, we will substitute them into equation number 2, and that is going to be the solution of given equation. So in the next step, I have put these values of 6 and 7. 6 means value of capital X, 7 means value of capital Y, that I have put in this product solution, which we have assumed, and we had given this as number 1. So Z equal to value of capital X into value of capital Y. Now this I have rewritten. I multiply this term with this and I combine these two constants. Similarly, C2 into C3 into these two functions. I have kept this function outside. I have just multiplied this bracket by C3, so that I can write C1 into C3 equal to some another arbitrary constant, C2 into C3 equal to say another arbitrary constant, that I have denoted by capital A and capital B. So this is our required solution. Equation number 8 is the solution of given homogeneous linear partial differential equation. So this is very easy method. It is applicable if our partial differential equation is homogeneous as well as linear, and we started by assuming that solution is the product of two functions, one function of small x and another function of small y, and then we used the assumption, this is our assumption, that solution is in this form, and because this is the solution, it will satisfy given equation. So we find out partial derivatives, whatever partial derivatives are there in the given equation, that we find out, we substitute their values in the given equation, and after simplifying we find two ordinary differential equations in capital X and in capital Y. And using the methods of solving ordinary differential equations, we are able to decide values of capital X and capital Y, and finally our solution is the product of these two functions, capital X and capital Y. So these steps are going to remain common for every problem of this method. What you have to remember is, you start with the assumption that solution is in this form. Suppose your equation is given in this form, say del u by del x equal to 2 times del square u by del t square. Then here partial derivatives are given for variable u. So your dependent variable is u, and partial derivatives are with respect to small x and small t. So independent variables are small x and small t. So here I will start with capital X and capital T, where capital X is a function of small x and capital T is a function of small t. Now here I will see I require first order partial derivative with respect to x. So I will write del u by del x equal to say x dash into t. I will consider t as constant, derivative of x with respect to x. Then I will require del u by del t. So x constant, derivative of t with respect to small t, I denote it by t dash. Then I again require second order derivative with respect to t. So x is as it is. Here I have to write t double dash. So I will substitute these two in this equation, and after simplification I will have this type of equation in capital X and capital T. On one side I will have function of x, on another side I will have function of small t, and those two functions are equal if and only if they both are equal to some constant. So then equating these two to that constant, we will obtain two ordinary differential equations in two variables, and after solving those two ordinary differential equations, we will be able to determine the solution of given partial differential equation. So this is very easy method, and they generally ask one question on the method of separation of variables every time in the GTU exam. So we will be discussing this type of problems in upcoming lectures. Thanks for watching.